Well, I will begin with a word of prayer. So, dear Father, we thank you for this day again. I thank you for this class and this time we have to meet and study your creation. Just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so we are talking about vector calculus. What is vector calculus? Well, vector calculus in a nutshell is the study of vector fields and their change, I suppose. So to start with, we probably should talk just a little bit more about like what is a vector field, right? For the most part, we're in 3 dimensions. We do some 2-dimensional things, but primarily 3 dimensions. So a vector field, and we talked about this a little bit already, right? But what's a vector field? Something like f of x comma y comma z. We could write it like this: p, q, and r, right? These are what? Like this is also p x hat plus q y hat plus r z hat. The component functions P and Q and R are all functions of X, Y, and Z generally. Right? So we talked about vector fields along a curve when we studied the Frenet frame in here, right? So we know about that, but now we're thinking about vector fields that perhaps fill all of space, right? And so perhaps it's just good to give some examples, right? So, example 1, here's a really boring one. You could just have the vector field f equals to x hat, right? Actually, x hat is hard for me to draw. Let me do z hat instead. That one's easier, right? So that's a kind of boring vector field. That's a constant vector field. How does it work? So the constant vector field, I mean, how do you visualize a vector field? That's really the question I'm asking. And I mean, there are various strategies, but one is to just, every so often kind of make a grid of points and just illustrate the, the vector just by plotting it in 3. I mean, how many of these do you need to draw? I don't know, but they're all z hat, right? So that's a constant vector field. In this case, P, Q, and R are what? Oh, my bad. Yeah. P and Q are both. P and Q are 0, and R is equal to 1. So it's kind of boring example. Let's look at a more interesting example. Example 2. What if we had f of, x comma y comma z equal to, well, we could just do x, y, and then 0, right? And we could try to plot that vector field. I'm just going to spend a few minutes just plotting some examples before I do any more calculus, because I think, that's kind of a helpful exercise for us, just to get our bearings here, what we're looking at. So, all right, so to visualize this vector field, it's doing what? It's always, wherever you plot it, right, it's doing what? Like, so here it would be going like this, right? Over here, it's going like that. Here it's, I mean, I can't draw worth anything, but if in the plane, oh man, it's miserable. Let me not even try these ones. All right, but if I go up, maybe I should draw a circle for reference, right? On this circle, it's going out like that, like that, like that, back like that, over like this. And I don't know, my picture doesn't do it justice. These are all, yeah, all horizontal, or if you will, that was what you said was better, parallel to xy plane. Right, so like, this is the one thing we can do is we could we can draw like little sample vectors to illustrate like the pattern of the vector field, right? And I mean, that's okay. Okay, so let's see here. What this one has what? P equals to X, Q equal to Y, and R in this case is equal to 0, right? Now, PQR is like, that's the typical notation used in like common calculus books, like Stewart, for example, will tend to use PQR. I sometimes prefer like F1, F2, F3, right? Like the other way we could decompose this would be something like the sum I equals 1 to 3 of F sub I x hat I, right? Like that's a kind of a more uniform notational scheme for the vector field. All right, so another example. We could look at f of xyz equal to, well, let's say x, y, z divided by the square root of x squared plus y squared plus z squared. So that vector field's a little bit more interesting, right? What can you tell me about this one? What's the length of this vector field at any point? 1. Right, because it's, well, except one point, right? Where is it? It's not defined where 0, right? But if I was to foolishly attempt to plot this thing, it's, you know, it's like this here, it's like that there, it's this, it's that, it's that. I mean, I don't know. My picture doesn't really do it justice, right? I mean, it is coming out at you. It's going every different possible direction. It's the spherically out. We have a name for this. What is this? Well, these are all normals to the unit sphere. That's true. But this has a name, right? This is what we call rho hat, right? It's the unit vector in increasing radial direction, right? That's in fact rho hat. This one, the example 2, if you take a look back, you could have written this as the square root of x squared plus y squared times, you know, like x, y, 0 divided by the square root of x squared plus y squared, right? And if you do that, maybe you could recognize that what you're looking at here is r hat. That is the vector field which points radially outward from the z-axis, right? And its magnitude depends on how far you are from the z-axis, right? So if I had, you know, tried to draw more of these, if I was further out, right, then the vector field's like, you know, it's bigger out here, right? But I think you can tell that these kinds of pictures are of limited utility to communicate, you know, quantitative aspects of the vector field, right? So it's useful to have another concept to understand vector fields, right? And the other concept that we should talk about is what's called a field line. You guys ever talked about field lines before? Sometimes they're called streamlines. So let's talk about that. So definition, a streamline or field line, or as it's sometimes called, integral curve, to vector field f is a path, let's say t maps to r of t, for which f of r of t is equal to dr dt. Let me draw a picture of what I'm talking about there. So if this was if these were integral curves of the vector field, all right? then what that means is that if we look at any point, right, then the tangent direction to this line is the vector field in question, all right? In other words, what this says is that the tangent field, to the integral curve is the vector field in question, right? What are the integral curves for my example 3? They're what? The normal. No, what do you mean normal? Normal. There's no surface here. I mean, you're not wrong. They're the normal lines to the unit sphere. Sure. I mean, but what I was fishing for is just simply lines from the origin. The field lines here are simply lines that are radially out from the origin, right? And these kinds of pictures are how we do physics. In physics, oftentimes we visualize a vector field in terms of its flow lines, in terms of its streamlines, if you like. Like, see if I can. All right, so like example 4. Excuse me. So here's some examples from physics, all right? Number 1, the electric field is Q over 4 pi epsilon naught. In our notation, 1 over rho squared, rho hat. So what this is the Coulomb field. If I wanted to visualize it, it just is going out from the origin every different which way, right? Like, oh man, I just got done talking about field lines. Let me use my field lines, dummy. Me, not you. All right, so the field lines to the electric field are like this. And to properly visualize this, understand that they're going in every direction, right? Every different direction they're going. And they're symmetrically spread out if I made my picture right, all right? Like there's an even distribution of the field lines. So the way that physics studies vector fields is that the field lines, the way we do it, is the density of the field lines is representative of the magnitude of the vector field. The more dense the field lines, the stronger the magnitude. And you can kind of see that in this one. What's the deal here? Magnitude is what? Follows what? The inverse square law. What happens to the magnitude of the electric field as you go to where's the charge in this picture, by the way? In the center, right? So Q is right there. So basically, electrostatics is the study of, electric forces between, positive and negative charges. And the rules for the electric field are that all of the field lines start at positive charges, and they can terminate at negative charges, or they can go on and on. All right, but basically, wherever the field lines are starting from, you can be sure that's where a charge is. All right, and so you see that the density of field lines is most dense where, like right close to the charge, which is actually also where this formula does what? As rho goes to 0, what happens to the magnitude of the electric field? Yeah, it does. I mean, it blows up to infinity, right? So is there something wrong with the formula? Well, this is a question people still debate. Now, so that's the Coulomb field. This is also the same formula for the gravitational force, right? Like the gravitational force field, force of gravity, is minus g m1 m2 divided by rho squared, rho hat. So this is Newton's universal, I can't spell universal. All right, universal law of gravitation. Again, it's an inverse square law, but okay, so like that was the Coulomb field, right? The electric force, in contrast, like the electric force looks like this: Q1, Q2 over 4 pi epsilon naught. That's a particular constant of nature, 1 over rho squared, rho hat. If I had a charge, if this was Q1, let's say, all right, so this is the electric field due to Q1, then Q2 would be another charge over here, right? And the force that is on Q2 is what I've written the formula for, all right? So you notice that if the charges are positive, they're both positive, then the force is in the r hat, the rho hat direction, right? It's away from the origin. In other words, the force is repulsive, for like charges repulse, right? If Q1 and Q2 if Q2 is negative and Q1 is positive, as I've indicated by the field line diagram here, then that puts a minus here, which means that the force is attractive, right? So electric forces are either repulsive or attractive, both are possible. Gravity, on the other hand, mass is the analog of charge for gravity. And so the gravitational charges are always positive, you could say. Masses are positive, which means that the force of gravity is always attractive, right? Same mathematics, though. It's the inverse square law. This is an important example for us, and we'll spend a fair amount of time trying to analyze the inverse square law and understanding it as deeply as we can, all right? Another important example from physics, if you have a long straight current, oops, let me make it go in the right way. So suppose you have a long, steady current, all right, steady current, I, which is equal to, say, I z hat. So this is a steady current in, z hat direction. Physics suggests that the field lines for this are circles which loop around like this. And the right-hand rule indicates the direction of the loops like that. All right. If I make it picture easier for me to picture, if I draw the current coming out at you, the field lines are like circles. All right. And so what I mean by this field line is, like, if you take a particular point, you get the magnetic field going like this. I can't. Come on, marker, do your thing. All right. But it's much easier to draw field lines as opposed to magnetic fields, right? What's the formula in this case? The formula in this case, for a long steady current, we can derive this by something called Ampere's law. It's equal to mu naught I over 2 pi r hat. Oops, that's not right. That's not r hat. What is that? What vector field encircles the z-axis? It's pointing in the direction of increasing what angle? Theta hat. Right, so the formula here is mu naught I over 2 pi r theta hat. Yeah. There are other things. If instead of having, another important example from electrostatics is if you just have a line charge like lambda, so that's say dq dz, uniform line charge, if that's the case, all right? So that's not a current, but just a charge smeared out over a line, an infinite line. Then the electric field in that case, it turns out it's lambda over 2 pi epsilon naught r hat over r. So that's the electric field for a infinite line charge. You notice that the magnitude of that electric field, it's exactly the same pattern as you see for the magnetic field from a long steady current, right? They're both what? They're reciprocal in the distance from the z-axis, right? That's what r is. R is what? For us here, r is the square root of x squared plus y squared, right? That's the distance to z-axis, right? That's what that means geometrically. All right, so my point to you is that in physics we study all kinds of vector fields, all right? Especially for electromagnetism, the study of electric and magnetic fields, it's the whole course, really. It's all about vector fields. Now, vector fields are also present in Physics 1, but they're a little bit less, they're not the center stage of the story, but the electric and magnetic fields are the center stage of the story for Physics 2, which is part of the reason it's good if you're taking this course before you take Physics 2. Yeah. But we can never implement this as like a curriculum requirement because it would make engineers graduate in like 7 years or whatever. So we don't want that. So yeah. All right, so those are some examples for you. Now, can you guys tell me, setting aside, there are other examples from physics. This is just a sampling, right? I mean, another important example is like if you just look at, say, water in a river or something, right? You could study the velocity field of the water molecules, right? That would define a vector field. That would define a vector field that the meaning of the integral curves would literally be flow lines, right? If you dropped a little bit of dye into the river, you watch where the dye traced out, that would trace out the integral curve, which would be the flow line of the velocity field. That's sometimes a useful bit of intuition. Much of the basic laws of electromagnetism were in fact discovered by that kind of analogy by a fellow named Faraday, who literally thought of electric and magnetic field lines as being physical entities that were kind of filling space. There's some debate as to whether or not they're, a mathematical construct or if they're more than that. I think they represent some kind of objective physical reality, but like everything else in physics, I think that that's just a partial story, because physics is not true. It's an approximation always. But anyway, yes, sir.
So in example 4 for I'm just going to use the current example, through the line, the straight line.
Yeah.
The streamline or the field line is the B vector, correct?
The streamlines for this example, the long steady current, the streamlines are circles that are around the z-axis, centered on the z-axis. There's infinitely many of them.
Yeah. So, and then we find the streamline through our definition over here.
No, we don't do that.
Okay.
The reason we don't do that, that's okay, truth in advertising here. Why don't we just find the streamlines then, right? Guys, can you understand why we don't do that? Like, why don't we just find the streamlines and understand everything from that? Well, the trouble with that for PQR is that this translates into dx dt is equal to P, dy dt is equal to Q, and dz dt is equal to R. See, so to find the integral curves, guess what you got to do? I mean, to do it directly, you'd have to solve this system of differential equations. But the bad news is, well, by the way, what is P, Q, and R for the Coulomb field? For example. It looks all nice and pretty if we use spherical coordinates. What's it look like in Cartesians? like the Coulomb field, E, Q over 4 pi epsilon naught, rho hat over rho squared. I like to write this instead as Q over 4 pi epsilon naught xyz divided by the square root of x squared plus y squared plus z squared. Well, forget the square root. Let's just write x squared plus y squared plus z squared to the 3/2 power. That's how that translates into Cartesian coordinates. Or in my usual notation, I might write this like q over 4 pi epsilon naught. Oh, well. See, this is where physics gets annoying, because I'd really like to write the equation r divided by r cubed. This is what I'll write. I got to put big old quotes around this, all right? Because that's not our notation in here at the moment, because we use r for what? For what? Say what you said again. I just didn't hear it.
Radius.
Radius. Which radius, though? Yeah, the polar radius. That formula is using r for the spherical radius. Now, do other people use r for the spherical radius? Oh, yes. Yes, they do, right? But I'm trying to be dogmatic in sticking to, as much as I can, rho for the spherical radius, r for the cylindrical radius in here. Yeah.
Can you just replace r with rho if it's the spherical radius?
Sure, that's what I did here.
So why is it rho hat over rho squared, and then it's r vector over?
Because r vector is not a unit vector. It's a vector of length rho.
Yeah.
So r vector, like the secret sauce here is just that the position is the distance from the origin times the unit vector in the direction out from the origin. So that's my, yeah. But do you see how horrible this is? You're going to solve dx dt as x over this 30/2 power of x squared plus y squared plus z squared. You got to solve dy dt equals to y over x squared plus y squared plus z squared to the 3. This is a nasty system of differential equations, and yet the answer's nice. I mean, it's lines from the origin. But anyway, this is not a question for here, though. This is a question for differential equations. And even there, it's too hard for us. So I'm not sure where that question belongs, but I mean, don't get me wrong. In differential equations, I will teach you how to find integral curves in the plane. Finding integral curves to two-dimensional vector fields, there's certain tricks that are special to the plane that make it very accessible. All right, it's actually no harder than like solving separation of variables problems. Yeah.
So in this course right now, we're not going to be tackling the deriving.
We need to be able to visualize the field lines, but we don't actually need to be able to find them.
Okay.
So like typically in here, I give you a formula for a vector field. It's important for you to be able to visualize the field lines to understand the geometry of the field.
Okay.
So that's all I'm after at the moment here in this introductory story arc. Just how can we picture vector fields? And I think the key ingredients for me are the notion of field lines. Also, the use of the non-Cartesian coordinate frame is very helpful because we have a name for this thing that goes outward in every way, every direction radially. That's rho hat, right? The thing that goes cylindrically around the z-axis, that's theta hat, right? Don't ask me what physics problem brings up phi hat. Like, I don't know right off. I'd have to think hard about that, but I'm sure there's one. Anyway, I'm teaching the junior level electromagnetism course at the moment, and I can assure you we're awash in the spherical and cylindrical coordinate frame. It's just everywhere, all right? So, physics aside, mathematically, is there a way we can produce vector fields? So that's a question. How can we construct? I was trying to spell construct there. Construct vector fields. All right, so one is we just write down the formula, right? just make stuff up, right? That's an option. For example, here, I'll ask you guys. Give me a function of x, y, z. No? Nobody?
X cubed plus y to the fourth over z e to the z.
Oh, e to the z. Oh, very interesting. I wasn't expecting that. How about the y component then?
Why?
Y. And the z component, what do we want?
Y over x squared.
Y over x squared. I like it. All right. So that's interesting. I have no earthly idea what the field lines look like for this, and nor do I want to find out. All right? However, there is an interesting question we can ask here. And like, what's one of the first things you're thinking? Think back to pre-calculus. What did you do? You studied how to graph them, which is what I was kind of talking about with field lines, right? And then one of the next things you talk about is the domain, right? So we can also have that idea here. What's the domain of the vector field? Let me just put it this way. It's all x, y, z such that formula makes sense. Formulas make sense, right? And so that's x, y, z for my example here such that what? Now e to the z, that's harmless. E to the z is positive, right? That can't harm us. That division by that, it's never division by 0. But this right here, that's a spicy meatball right there. If x is equal to 0, you're in trouble. So we need x not equal to 0. So the domain of this vector field is all x not 0. What was the domain of the Coulomb field?
All numbers except
We call this punctured 3 space. It's like 3 space with the origin removed. Boop. What's the domain of the magnetic field for a long steady current? All of 3 space except for 0 is not quite good enough. It's the right idea. What do you mean 0 though?
0, 0,
0, 0, 0 is part of it, but not enough. The z-axis, right? All of our 3 with the z-axis deleted, because the z-axis is where the cylindrical radius is 0. All right? Now, a lot of the time, we can just kind of be freewheeling and not worry about the domain of a vector field, but every so often, domain is the whole issue. So keep this on your radar. Domain of vector field matters. So one thing is we could just make stuff up, right? But another way, we could use nabla, right? Like, what if we take nabla of, oh, I don't know, 1 over the square root of x squared plus y squared plus z squared. What's that? We know how that works, right? So we've got partial x of 1 over rho, right? Partial y of 1 over rho. Partial z of 1 over rho. Which gives us minus 1 over rho squared by the chain rule. And then you got to deal with whatever partial x, partial rho, partial x, partial rho, partial y, partial rho, partial z. I'm just streamlining the calculation. It's the same chain rule every time, right? We always got a minus 1 over rho squared, but the chain rule leaves us with partial rho, partial x, partial rho, partial y, partial rho, partial z. Well, what are those? You can work them out. And if you do, that gives us x over rho, y over rho, z over rho. In fact, we worked these out before in homework or class. All right, this is an example I'm begging. I mean, we've done this example before. So what I got is I've got minus 1 over rho squared rho hat is what I have. That's almost the Coulomb field. I mean, it is the Coulomb field, but the inward-seeking Coulomb field, right? let's do an easier example. What if we took the gradient of, xy plus z squared? What would that be? We got what? We got y, then x, and then 2z, right? So another way we could construct vector fields, perhaps, is to take the gradient of a function. What's the significance of the gradient vector field for a function? What does it tell you about the function? Level curve. Well, it has to do with the level curve or the level surface, right? It points perpendicular to the level surface. In the context of 2 dimensions, yes, it points perpendicular to the level curve, but its significance as it relates to the function which we're differentiating is that the gradient vector field points in the direction in which you want to level up, right? So like the gradient of 1 over, this is, by the way, the gradient of 1 over rho. And so if you want to increase 1 over rho, which direction do you go? You go toward the origin, right? Because it blows up to infinity there. That make sense? So the gradient vector field points in the direction of increasing the function which you're calculating the gradient of. This brings us to a natural question, right? Is every vector field like this? Right? I just constructed 2 vectors. I showed you essentially that the Coulomb field is such a field. It can be calculated as the gradient of another vector field, right? It could be the gradient of a function. Is every vector field like this? In other words, is it always possible to calculate this as the gradient of some so-called potential function f? If you think back to the homework that you've worked out, the answer is no. We've explored this issue in homework. We saw that no, not every vector field can be written as the gradient of some other function. The reason being that to be the gradient of the function, it requires certain interdependence between the different components of the vector field, right? We want to understand this more deeply. This is another thing we're going to look at harder. If this is possible, that makes the vector field what's called a conservative vector field. So I've showed you today, through this little calculation, that in fact the Coulomb field is a conservative vector field because it can be written as the gradient of a potential function. All right. So those are some of the questions that we're interested in. Now, I mean, there are other ways of constructing vector fields, like you could use the Frenet frame to construct vector fields from curves. Like you could do that kind of thing, right? I mean, listen, what a vector field is simply an assignment of a vector at each point in space. How many different ways are there to assign a vector at each point in space? There's like as many as your imagination permits, right? This is an endless pursuit. But I've just showed you, I think, if you can write the vector field as the gradient of a function, that's pretty neat. All right, so what comes next after you've talked about geometry and a little bit about domain? We usually like to start talking about calculus. And so for the vector fields, there's really three kinds of calculus differentiation we can talk about. So derivatives. So number one, the gradient of f is equal to partial f, partial x, partial f, partial y, partial f, partial z, right? This is the first chapter, first subplot, if you will, in the story of the differential vector calculus. We've already told this story, but it's part of this. There's a nice formula here. We can write this as, of course, the sum I equals 1 to 3 of partial f, partial xi, x hat I, right? So there's a nice slick formula for the gradient. So that's point number. That's it. First thing we can do, gradient. Second thing we can do with nabla is we can calculate the divergence. Nabla dot vector field. This is Well, okay, so it's partial p partial x plus partial q partial y plus partial r partial z, or perhaps more elegantly, it's the sum I equals 1 to 3 of partial f sub I partial x sub I, where I'm assuming that f is the PQR vector, or if you like the other notation, sum I equals 1 to 3 of f sub I x hat sub I. This is the so-called divergence of f. Right? Notice that the divergence is generally like a scalar function. All right? Yep.
Why is it called divergence?
It describes how the vector field's diverging, yeah. But the full answer to that will be given over the period of like 4 lectures. There's a lot to say there. I mean, for example, the Coulomb field, if we were to calculate the divergence for the Coulomb field, you'd find well, let's not do that. That's a complicated thing. Let's start with the easy thing. So like, for example, where am I? Example 5. If I have f of x, y, z equal to, well, let's say x squared plus y, oh man, what's wrong with me? Vector field, right? Here, we'll keep it real simple, x, y, z, right? That's one of the stupidest and simplest vector fields you can think about, just the position vector field, right? It points radially out from the origin, and the length of it is how far you are from the origin, right? What's the divergence of this thing? I heard 3. Do you guys agree? And how about my next example? Zero, right. It turns out that, so here's the thing I stopped half sentence. You work it out, and this is not entirely an easy calculation. It'll take you about 5 minutes to do carefully. But if you calculate the divergence of the Coulomb field, it's actually 0 on its domain. And yet, to my common sense of what the word diverge means, it seems like this vector field's diverging, right? Spreading out. So whatever divergence is measuring, it's not simply that the vector field's spreading out, it's more than that. Now, you notice I used the word domain there. That's the issue, right? What's the domain of the Coulomb field? Anyway, I don't want to ruin this story for you. I'm gonna stop this discussion. We'll go back to this. We'll go back to this. All right, so 3. What else can you do? You can, calculate the gradient vector field. You calculate the divergence of a vector field. But there is also the cross product, and that would bring us to the curl of the vector field. And my preferred formula for this is the sum ijk equals 1 to 3 of epsilon ijk, and then you got yourself a partial I f sub j, and you put that thing in the x hat k direction. Now what that means is partial 2 f3 minus partial 3 f2 partial 3 f1 minus partial 1 f3 partial 1 f2 minus partial 2 f1, where partial I is my shorthand for partial xi. x1 is x, x2 is y, x3 is z, if you didn't realize. That's the curl of a vector field. Now you can ask me, what does that mean geometrically? And the answer is, it says something about a vector field curling around something. It's kind of like that. Like we can calculate the curl of, what's the curl of f1? And what's the curl of f2 here? Look at how the formula, it's just like the cross product, right? See how the first component involves 2 and 3. The second component involves 1 and 3. The third component involves 1 and 2, right? So for f1, the first component is x. The second component is y. The third component is z. So all of those derivatives are necessarily 0 because you can't have, like, the curl of f1 is just 0. And I say the 0 vector. How about the curl of f2? Let me write down the non-trivial terms. So we've got, let's see here, partial y. No, not that one. Partial. Oh, that's not. I guess this is just 0, the first one. Let's see here, partial. Oh, minus. No, that one's just 0. Sorry, I'll eventually get something. That one is partial x of f2, but f2 here is x. And then minus partial y of f1, which was minus y, which is actually 0, 0, 2. Do you guys know what f2 looks like? Sometimes it's called the pinwheel field. Its integral curves are like circles, like that. And the way it's working is it's, let's see here. It's easier for me to do it like this. Look at it. So here's the z-axis coming out at you. So if we go, I think it's like this. Something like that. I may have it. I should check. If this point is, if this is the z-x-axis and this is the y-axis, am I right? What's up with that? The class is not even over. Dudes, seriously. So 2, that points in the direction of the axis around which it's curling. See this vector field, it like curls around the z-axis, and the curl was 0, 0, 2 because it's wrapping around like that. So it's something like that. But anyway, this is just the start. We have much more to say. I'll give you guys back your test. So.